Okay, let's talk about motion of a magnetic moment in an external magnetic field. There is a common wisdom that if we put a magnetic moment into a magnetic field, then it will start to precess, as it is shown in this figure. For further mathematical treatment, it is convenient to make this figure a little bit more abstract and to introduce a coordinate system, where magnetic field B is oriented along the z-axis of the laboratory frame and the magnetic moment N precess around the z-axis. My goal in this video is to provide a basic mathematical explanation for such kind of motion. There are different ways how to do this. Basically, it depends whether we want to use quantum mechanical or classical theory for this purpose. Okay, let's start with the classical mechanic first. The Newton law for the rotational motion says that the time derivative of the angular momentum of a rotating body is equal to the torque applied to this body. Commonly, angular momentum of a body and the magnetic moment of the body are proportional. Hence, we can say that L is equal to m divided by some constant gamma, which is called gyromagnetic ratio. Furthermore, if we have a magnetic moment in the magnetic field, then this magnetic field exerts a torque on the magnetic moment, which is equal to a vector product of m and b. By inserting the expression for the angular momentum L and for the torque T into the dynamic equations, I obtained the equation for the dynamics of magnetic moment m in magnetic field. In order to solve this equation, it is convenient to introduce a rotating frame x-stroke, y-stroke, z-stroke, which rotate in the laboratory frame xyz with the frequency omega. I will rewrite the dynamic equation in the new rotating frame. Here I will take into the account that the time derivative of any time-dependent vector computed in the laboratory frame and its time derivative computed in the rotating frame are related by the following relation, where m-stroke is the magnetization vector in the rotating frame. Additionally, if we take into account that the magnetic field B is equal in both frames, then we'll get the following dynamic equation in the rotating frame. This equation can be rewritten in the form very similar to the initial form of the dynamic equation. The only difference here is that the magnetic field B is changed with the sum of magnetic field B and omega divided by gamma. Now, if we choose the angular velocity omega of the rotating frame equal to minus gamma b, then we'll come to an interesting result. From this dynamic equation, we obtain immediately that the time derivative of magnetization vector m-stroke is equal to 0. It means that the magnetization vector m-stroke is constant in the rotating frame. In terms, it means that the magnetization vector m rotates with the constant angular velocity minus gamma b in the laboratory frame. This knowledge allows me to determine time dependence of the magnetization vector components in the laboratory frame. We have mx equal to m0 cosine omega t and my is equal to m0 sinus omega t, where m0 is the magnitude of the magnetization. The z component of the magnetization remains constant since the rotation is made around the z-axis. With this, I would like to finish the explanation of magnetic moment motion in an external magnetic field based on a classical theory. Another approach to describe magnetic moment motion in magnetic field is based on quantum mechanics. Actually, it is necessary to use it when we deal with quantum mechanical systems. Noticeably, both approaches give us similar results for some cases. I will demonstrate the usage of quantum mechanics for the description of magnetic moment motion originating from a particle with a spin 1/2, which can be an electron or a proton. In such cases, as we know, spin projection can have two values, plus 1/2 or minus 1/2, and the wave function of such particle is a two-component function. The wave function psi is determined by the Schrödinger equation with the Hamiltonian H describing the interaction of magnetic moment with the magnetic field B, which is a scalar product of vectors m and b. As in the classical case, here we also assume that the magnetic moment operator m is proportional to the angular momentum operator L via the coefficient gamma. And angular momentum operator L can be expressed via the vector spin operator S, which is basically proportional to Pauli matrices for spin 1/2 particle. Now, by inserting expression for L into the expression for M and expression for M into the expression for Hamiltonian, taking into the account that magnetic field B is oriented along the z-axis, and Hamiltonian into the Schrödinger equation, we can rewrite the Schrödinger equation in the following form. I d psi over dt is equal to omega sz psi, where omega is equal to minus gamma b, as it was in the classical case. Sz is the corresponding spin projection operator, which can be given by a diagonal matrix 1/2 minus 1/2, which has two eigenvalues 1, 0 and 0, 1. A general solution of this equation can be written as a linear combination of vectors spin up and spin down with the time-dependent coefficients a1 and a2. The coefficients capital A1 of t is equal to some constant small a1 multiplied with e to the power minus I omega divided by 2 multiplied by t. The time-dependent coefficient a2 of t is given by a similar expression, but the exponential function is complex conjugated here. This solution can be easily verified by inserting the function psi into the Schrödinger equation. Due to wave function normalization, we can impose additional conditions on the coefficients a1 and a2. Now we can give few examples of the coefficients a1 and a2 which satisfy the last conditions and the wave function which is obtained for such coefficients. The first example is a1 is equal to 1 and a2 is equal to 0, which yields the wave function psi equal to e to the power of minus I omega divided by 2 multiplied by t and multiplied by the spin up vector. The second example is very similar to the first example, with the only difference that now a1 is equal to 0 and a2 is equal to 1, which yields the wave function psi equal to e to the power of I omega divided by 2 multiplied by t and multiplied by the spin down vector. And the third example is when the both coefficients a1 and a2 are equal to to 1 over square root of 2. This gives us a wave function which is proportional to the sum of the wave function from the example 1 and 2. This result shows us how to construct the wave function of a spin 1/2 particle in a magnetic field. Now we can use the obtained wave function to calculate the components of magnetic moment operators via the standard quantum mechanical formulas. It is convenient to introduce rising and lowering spin operator S plus and S minus, which can be later used to calculate expectation value mx and my. Just to remind, the action of the S plus operator on the spin-up vector is 0. The action of the S plus operator on the spin-down vector gives us spin-up vector. Similarly with the spin-minus operator, the action of the spin-minus operator on the spin-up vector gives us spin-down vector, and the action of S minus on the spin-down vector yields 0. Using S plus and S minus operator, we can easily determine Sx and Sy operators and their expectation values, which are proportional to the magnetic moment components mx and my respectively. Hence, we obtain. Okay, let us calculate now the expectation value of the operator S plus for the wave function obtained at the previous slide. By direct insert of the general form of the wave function psi into this formula, we obtain the following expression. Taking into the account the rule mentioned above and the orthogonality of the spin-up and spin-down vectors, the last expression can be simplified to the following form. Just to remind, the orthogonality conditions means that such scalar products are equal to 0. Now we can calculate the expectation value of the S plus operator for some specified cases. We will consider the three wave functions which were obtained at the previous slide. It is clear that in the first and the second case, the S plus expectation value is equal to 0, because in these cases either coefficients A1 or coefficient A2 are equal to 0. In the third case, we have the capital A1 equal to the 1 over square root of 2 multiplied by the exponential function, and the capital A2 coefficient is equal to the complex conjugated A1. Now, inserting A1 and A2 into this expression and taking into account that the expression in bracket is equal to 1, we obtain S plus expectation value equal to 1/2 e to the power I omega t, and S minus expectation value equal to 1/2 e to the power of minus I omega t. Now, inserting the expectation values S plus and S minus into this formula, we obtain the expectation value for mx and my. We see that expectation value mx is proportional to cosine omega t, and the expectation value of mi is proportional to sinus omega t. The z component of magnetic moment remain constant. These results, which can be interpreted as a precession of magnetic moment in magnetic field, are very similar to the results which were obtained using classical theory. Okay, let's make the next step. In this lecture until now, I have explained how precession of magnetic moment can be derived A. Based on the classical dynamics and B. Based on quantum mechanical theory using Schrödinger equation, wave function and concept of spin. Now I want to show another description of magnetic moment precession based on quantum statistics, which is basically an elaboration of quantum mechanical approach. In quantum statistics, the state of a system, a large system which consists of an ensemble of equivalent elementary systems, is described by the density matrix instead of wave function. The expectation value of an observable O is calculated as a trace of the density matrix multiplied by the operator of this observable. Generally, the density matrix ρ is defined as an average product of the coefficients Ai, Aj, which determine the wave function of pure quantum mechanical states of elementary systems which enter the large ensemble. In order to explain this definition, I will bring an example. Let's say we have an ensemble which consists to 75% out of systems in the pure quantum mechanical state 1, which I have introduced before, and to 25% out of the systems in the pure quantum mechanical state 2. To be more specific, we are talking here about an ensemble of systems of isolated spin 1/2. Then we have rho ij is equal to 0.75 ai aj coefficients of the first wave function plus 0.25 ai aj coefficients of the second wave function. With this, we obtain for the density matrix a diagonal matrix with the 3/4 and 1/4 at the diagonal. Noticeably, this density matrix cannot be constructed of a single pure quantum mechanical state like this, which is determined by two coefficients, B1 and B2. In other words, we cannot obtain this density matrix just with the coefficients B1 and B2 according to this rule. We can prove this statement by contradiction. Okay, let's assume that we can construct such a density matrix with zero off-diagonal elements, just from B1 and B2. In this case, we will have that B1 multiplied by B1 star is equal to 3/4, which means B1 is not equal to 0. Also, B2 multiplied by B2 star is equal to 1/4, which means that B2 is also not equal to 0. It means that B1 multiplied by B2 stars, which is the off-diagonal element of our density matrix, is not equal to 0. But in our density matrix, the off-diagonal element is equal to 0. Hence, we have obtained an contradiction. Also, we come to the conclusion that in order to get such a density matrix with non-zero diagonal elements, we need to have an ensemble with the elementary systems in different pure quantum mechanical states. Okay, we can go further. The time evolution of the density matrix is determined by the Liouville von Neumann equation, which is similar to the Schrödinger equation. The solution of this equation is given by a so-called sandwich operator product, with the initial density matrix in the middle. This can be easily verified by direct insertion of the solution into the Liouville-von-Neumann equation. Now let's look at the initial density matrix. Since density matrix is a Hermitian matrix, and in our case it is a 2 by 2 matrix, we can present our initial matrix ρ of 0 as a linear combination of a unit matrix and spin operator matrices Sx, Sy, and Sz, which are proportional to the Pauli matrices. Now we will be even more specific. We will assume that our initial matrix is proportional just to Sx operator. That is, ρ of 0 is Bx multiplied by Sx. Now, inserting this expression and the Hamiltonian, which is in our case is just omega Sz, into this expression, we will obtain the density matrix at any time t from the initial density matrix. The obtained sandwich operator can be transformed in order to get rid of spin operator Sz from the arguments of the exponential functions. Since this transformation is of a pure mathematical nature, and their explanation would require a rather large deviation from the main topic of this video, I will skip them and just write the final result. Here we have the scalar constants Bx multiplied by a sum of the operator Sx multiplied by cosine omega t and operator Sy multiplied by sinus omega t. Now we can compute the expectation value of the x component of the magnetization, which is proportional to the expectation value of the Sx operator. For this, we will use this formula with the Sx operator instead of the operator O, and with this expression for the density matrix. By computing the traces of the products of the spin operators, we obtain that the mx is proportional to cosine omega t. Similarly, we obtain the expectation value of my proportional to sinus omega t. As we well know, such time dependencies of x and y component corresponds to the rotation or precession of the magnetization in the xy plane. Hence, we have obtained another explanation of the magnetic moment precession in magnetic field. Okay, now I would like to conclude this video lecture. In this video, I have shown 3 ways how to describe mathematically precession of magnetic moment in a magnetic field. The first method was based on classical theory, employing basically Newton's law for the description of motion of a magnetic moment. The second approach was quantum mechanical, which used Schrödinger equation and gave us magnetic moment time dependence as an expectation value of magnetic moment operator calculated with the obtained spin wave functions. And finally, a quantum statistical method which employs density matrix and Liouville-von-Neumann equation for the description of magnetic moment precession was introduced. Obviously, the last quantum statistical method is the most general. It accounts for quantum mechanical and temperature statistical effects, and it is mostly used in magnetic resonance. Although, due to its simplicity, The classical approach is also sometimes used to explain and describe some simpler aspects of spin dynamics in magnetic resonance. With this, I would like to finish this video lecture, to thank you for your attention and to invite you to watch other my videos related to spin dynamics, which are given in the description to this video. Bye.